Welcome back. Today we're focusing on lecture 4.2, Intermolecular Forces in the Dissolving Process, with an emphasis on intermolecular forces. But I do want to talk to you a little bit about the dissolving process, but first, let's go over the general theme of Unit 4. We want to be talking about this good gentleman over here, Fritz Haber. Fritz Haber might be the epitome of evil genius. He is both responsible for some of the greatest breakthroughs in modern history, especially in the agricultural world, and actually won a Nobel Prize for it. And he's also responsible for some of the most deadly creations that the world has ever seen. So go ahead and get some of his reading done, annotate it, bring it to me so that we can focus on the main concepts, the core concepts behind the chemistry that Fritz Haber was involved in. Today we're going to be focusing on a few things. We're going to discuss how ionic solids dissolve due to the random molecular motion of water molecules. We're also going to discuss the three main intermolecular forces: hydrogen bonding, dipole-dipole bonding, and van der Waals forces, also known as dispersion forces, as well as focusing on comparing and contrasting those intermolecular forces and how they're involved in the process of dissolving a solid. So, first things first, I'm wearing my chef's outfit today because I want to talk to you a little bit about the chemistry behind cooking pepperonis. I love cooking pepperonis, and I make pepperoni sandwiches all the time. I like a little bit of salami, a little bit of pepperoni, get some greens there, some spinach, olive oil, garlic salt, but that's just my preference. However, there's so much chemistry behind this that I have to go over it a little bit. So when I cook those pepperonis, you'll notice that the oils start to come out. Why is that? The reason is because like dissolves like. Things that are similar dissolve and interact with other things that are similar to it. And in this case, when we heat up these pepperonis, the fats in it are essentially rendered or melted so they can dissolve out some of the color and flavor compounds from the pepperoni. And in particular, it's going to take out all the fats and oils, which are just long carbon chains that get broken down when there's all this heat, and it pulls out some delicious substances like chili peppers and cinnamic acid, as well as paprika compounds that are usually incorporated into the pepperoni but come out when you cook it. And it's an explanation for the deliciousness. Now, that chemistry behind it has a lot to do with it, and the reason why they stay together is due to intermolecular forces. And what are intermolecular forces? Well, let's talk. Intermolecular forces are essentially just the forces that attract molecules to one another. The three main types that we're going to focus on here are hydrogen bonding, dipole-dipole forces, and dispersion forces, which we call van der Waals forces, which we'll talk about in depth. The first one you should know about is dipole-dipole forces. And we know that positives and negatives love to be attracted to one another. Dipole-dipole forces refer to the attraction between molecules that have what is known as a permanent dipole. And if you don't know what a permanent dipole is, let me show you. Dipoles result from one atom being bonded to another atom when there's a large difference in electronegativity. So something like hydrofluoric acid, we have hydrogen and fluorine. Now, fluorine is in the top right of the periodic table, making it a much more electronegative atom. It's much stronger. It pulls electrons towards it much more strongly than hydrogen does. Because of that, even though they're covalently bonded together and they're sharing, it's not an equal sharing. No, fluorine is much stronger, and so it's going to take the electron towards it more often. And since electrons are negative, that's going to create what's known as a partial negative charge, which we see here, the partial negative charge of fluorine, making it slightly negative, and hydrogen slightly positive. Not completely, but slightly. And this right here is a dipole. Dipoles essentially look like this, and they're actually attracted to one another because one side is positive, one side is slightly negative. They're both slightly positive, slightly negative. So when they're close to each other, a couple molecules are actually going to be attracted to each other. And this is dipole-dipole bonding. Partial negatives attracted to partial positives. Then we have dispersion forces. And dispersion forces are caused by temporary dipoles. And temporary dipoles result from the random motion of electrons. Electrons are zooming all over the place. So sometimes they're all going to be here, sometimes they're all going to be there, sometimes they're all spread out evenly. But when they're not spread out evenly, when there's an uneven distribution, it creates a very quick positive, slightly positive charge and a very quick, slightly negative charge. When a bunch of atoms are doing this, they actually get attracted to one another. And so there's a very quick, weak intermolecular force between them known as dispersion forces. And we also call these van der Waals forces. So usually, two hydrogen molecules, they share exactly evenly because they're both the same strength. But sometimes the electrons are moving around and they all sit on one side. And so then there's a temporary negative, or sometimes they all jet to the middle. And there's temporary negative charges on the insides, or maybe they jet to the outsides. There's temporary negative charges on the outsides. What this does, it creates a temporary dipole that pulls them together very quickly, and then they're released again. Attracted and released as the electrons randomly move about. The last one we want to focus on is the intermolecular forces that holds water together. We know that water has some weird properties, but what the heck? What is it that does this? This is known as hydrogen bonding. And hydrogen bonding is the strongest intermolecular force that we're going to talk about. It's the attraction of one molecule that contains hydrogen to another molecule. And when hydrogen is bonded to nitrogen, oxygen, or fluorine, sometimes known as the phone, F-O-N, there's a large difference in electronegativity. Fluorine, oxygen, and nitrogen are the only elements that will participate in hydrogen bonding. So you need hydrogen and you need one of the phones, F-O-N. Now this creates a partial positive and partial negative charge in the same way that dipole-dipole bonds do. So hydrogen bonding is actually the strongest form of a dipole-dipole bond. And the partial positive charge of hydrogen, because hydrogen is always less electronegative, and so electrons will be unevenly shared from the hydrogen to one of the phone elements, F-O-N, fluorine, oxygen, nitrogen. And when this happens, you get what's known as hydrogen bonding. And this is why water sticks to itself. Because you have oxygen and two hydrogens right in here. The oxygen is partially negative, both of the hydrogens are partially positive, and the oxygens all get attracted to the other hydrogens. And so water pulls itself together. And you can see that by putting a bunch of drops of water on a penny and watching them stick to each other. It's the other reason why if you turn a faucet off, there's a little drop that just kind of hangs from the top of the faucet, but won't fall, because it's still stuck to the water in the faucet. This is what a hydrogen bond looks like between water. So you have a water molecule here, a water molecule there, and they're just barely attracted to each other because of the partial positive and the partial negative. And this is the strongest intermolecular force, and one that you must know. Again, water bonding to itself via hydrogen bonding. So intermolecular forces essentially lead to the phase of the substance. So the least intermolecular forces are gases, because if they're not being held very closely together, they have the ability to spread out. However, when you have solids, there's a lot of intermolecular forces holding them together, keeping them in place, and therefore they stay in the solid phase. So go ahead and summarize that for me, guys, and take a second to look over your homework for 4.1 on intermolecular forces, and I hope this lesson helped. Have a good one.